Welcome to The Explainer. Today, we're diving into a concept that might completely flip how you think about writing software. If you've ever felt totally bogged down by endless validation checks, checking for nulls, verifying bounds, just trying to make sure a system is in a ready state before your actual logic can even start, well, you are in exactly the right place. We're unpacking the Invariant Avoidance Principle and really looking at exactly why invalid code remains impossible when you design your systems the right way.
Okay, let's dive right into this. Just imagine, for a second, a world entirely free of those endless validation checks and boilerplate code. What if, instead of writing dozens of lines just to guard your methods against bad data, the very structure of your code made invalid states completely unrepresentable? You wouldn't even need to check if something was wrong because the compiler simply wouldn't let it happen in the first place. Sounds pretty great, right?
The source points out that the pain you feel writing all those validation checks is actually a symptom of a much deeper design problem. These checks are basically just contractual obligations the caller is supposed to satisfy. And as the text reminds us, Murphy's Law is always in effect in software development. If an AVI allows a caller to pass bad data, like a null list or some negative index, it is absolutely inevitable that eventually someone's going to do exactly that. And usually it happens on a Friday afternoon right before your code crashes in production. To understand how to actually fix this, the source material asks us to look at the two main culprits causing architectural strain. First up, preconditions. These are the conditions that just have to be true before a method is even called. Think parameter ranges or your classic null checks. Second, we have class invariants. These are conditions that must remain true throughout the entire lifetime of an object, like, say, a cache total that must always perfectly match the sum of individual items. Every single one of these requires manual enforcement, really careful synchronization, and honestly, exhausting testing. So, to completely shift our paradigm here, the text offers this brilliant analogy. Think of a child's shape sorter toy. A round peg can only fit into a round hole. There are no written rules or instruction manuals for the toddler saying, hey, rotate the peg exactly 45 degrees before inserting. The physical shape of the toy makes incorrect insertion literally impossible. According to the principle we're looking at today, this is exactly how our APIs should act. So how do we actually build the shape sorter in our code? Well, the source breaks this down through a mechanism called state space reduction. Basically, every class or method has a total possible state space based on its types. For example, a nullable string includes all possible strings plus null. A precondition usually acts as a runtime filter to narrow that space down. But if we use really precise compile time types, we align the possible state space exactly with the valid state space right from the jump. We literally make our types the shape sorter. And you can really see the difference this makes in practice when you look at data extraction. Let's say you're writing a method that pulls data from a list using an index. If you pass a raw index parameter, you are forcing your code to handle out-of-bounds preconditions, leaving you totally vulnerable to runtime crashes. But if the method is designed to accept the exact validated object it needs, rather than just an index, you reduce those out-of-bounds preconditions to absolute zero. We're actually seeing this whole shape sorter mentality baked right into modern language design too. The text highlights how languages like Kotlin, Swift, and TypeScript strictly distinguish between nullable and non-nullable types. By simply declaring a method parameter as a non-null type, you completely eliminate the dreaded null check precondition. The compiler just does the heavy lifting for you, making a null pointer exception physically impossible at compile time. No runtime checks needed. Another huge area where the source applies this concept is in the classic battle of primitive obsession versus value objects. Instead of accepting a raw string that's supposed to represent a URL and then having to write complex parsing preconditions inside your method, you can simply require a compiled URL object. By doing this, the parsing constraint is handled exactly once during creation. That means all your downstream methods remain perfectly clean and entirely free of runtime checks. Let me share a quick war story from the source material that really drives home the danger of class invariance. Imagine a gaming application where the developers cached the player's health in 3 different UI components, just to avoid querying the database too often. Makes sense, right? Well, during a low bandwidth connection, one component failed to update after the player took damage. The result was that the game showed the player as dead with 0 HP on one part of the screen and happily alive with 50 HP on another part. Talk about a confusing user experience. The fix to that incredibly confusing health bar bug illustrates a really powerful technique, deriving state dynamically instead of caching redundant variables. Redundant fields inside a class create an invariant that requires perfect, super fragile synchronization.
If you calculate values dynamically instead, using a single source of truth and pushing updates reactively, you completely remove that class invariant. It makes that kind of desynchronization physically impossible. Now, the source does acknowledge we can't avoid invariants entirely. They're basically the heart of business logic. But we can strictly control them. The text gives us 4 highly practical management techniques to minimize and isolate these invariants in our daily code. They are: leverage non-nullable types, derive state instead of caching it, encapsulate inevitable invariants, and finally, use value objects.
Let's zoom in on the specific trade-off for using non-nullable types. The strategy recommended here is a simple 2-step process. Step 1, use non-null types strictly throughout your internal domain layers. Keep it tight. Then, step 2, isolate your null safety boundaries by performing your validations exactly once at the absolute edges of your system. So place those checks right at the HTTP or JSON interface boundary and keep your core logic completely clean. Looking at the impact analysis table provided in the text, the Invariant Avoidance Principle scores incredibly high on practical impact. I mean, it gets a massive 10 out of 10 for cross-platform relevance simply because it applies universally, from mobile apps to the backend all the way to UI states. It also significantly reduces the QA load by blocking invalid data combinations right at compile time. That's exactly why it scores so highly on team and process implications. So it all culminates in this final score, an 8.3 out of 10. The source categorizes this as a solid grade A principle. Minimizing preconditions isn't just some academic exercise. It is absolutely crucial for crash-resistant software design. It literally eliminates whole classes of runtime bugs, proving exactly why invalid code remains impossible when you force the compiler to do the validation for you. The text ties this all back beautifully to the rule of explicitness. Self-documenting code and highly specific parameter types work hand in hand with invariant avoidance. Using explicit value objects, like requiring that compiled URL type instead of just a raw string, is the primary way we eliminate those validation preconditions from our method bodies. It makes our code's intent crystal clear to any other developer who might be reading it down the line. By designing interfaces with fewer preconditions, the source shows us how we can create systems where correct usage is natural and incorrect usage is, well, physically impossible. But this leaves us with a fascinating question to chew on. If your models are now this simple and your state spaces are this perfectly reduced, where exactly do you draw your boundaries of change when business requirements inevitably evolve? That's a pretty provocative thought, and it leads perfectly into the single responsibility principle, which we'll be breaking down in our next explainer. See you then.